Been a long time since we talked about this, but let's get back to where we were. I want to remind you of something, and then I'm going to change the rules a bit. So, are you all ready? Well, ready or not, here we go. Let me just give you the quick recap. And I want to be very, very deliberate here. I am trying to ensure that you understand that there is a delicate balance that's necessary for an object to be in a circular orbit, and there's a couple of assumptions that we make. So let's talk about that balance for just a moment. For an object to be in a circular orbit, we'll say that we have a ship here and a planet here. For an object to be in a circular orbit, it must have a perfect tangential velocity that balances against a centripetal acceleration. We know what this relationship is. And in this relationship, I am purposely choosing the linear version of this relationship. That says for an object to travel in a circular path, it must be experiencing an acceleration that is directly proportional to the velocity squared divided by the radius of curvature. That's the balance. Now, in order for that balance to exist in an orbit, the unbalanced force on the spaceship has to be equal to MAC. All I'm doing is reproving something that we've already talked about, but you're supposed to be able to prove it yourself. Now, the left side, that unbalanced force, what causes that unbalanced force? Yes, sir?
Gravity.
Yes, sir? No, he was right. He said gravity. I was hoping you were just going to repeat it. Sorry.
I thought that was more specific.
No. Gravity's fine. Force of gravity is what I'd probably like to hear, but I asked what provides the force. Gravity is a good answer. So to calculate that gravity, we know we talk about two different objects, right? They create a force between them. So that would be the mass of the planet times the mass of the spaceship times g, all divided by the separation distance squared. I say it this way every time, and I don't know if you guys are even writing this stuff down. This is the separation distance from the center of the planet to the center of the ship. That's what we're saying is r. Be careful, though. This has to equal mvt squared over r. Now, what r is that? Is it the separation distance? What word would I normally use here? Radius of curvature. Same letter, different meanings. And which m is on the right side? The mass of the planet or the mass of the ship? Yes, sir? Mass of the ship. It's the thing that's going in the circle. It's the thing experiencing the unbalanced force, but they're both experiencing the unbalanced force. So you have to be careful here. We're talking about the ship, not the planet. If I was asking about the planet, then the mass of the planet would go here. However, are these two r's the same r? That's another question you're supposed to ask yourself. These two r's are only the same if the mass of the planet is much bigger than the mass of the ship. A question that you should be asking yourself. If they are not this proportion, if we're talking about something where they're not the same, well, then they're not the same r. And we'd have to be more careful. Now, if it's a circular orbit, certainly you can make this relationship, which means you can solve for something here. One of the things you can't do is you can't find the mass of the spaceship, right? It cancels out here. But you could certainly find the other things here, right? If I carefully watched an orbit, I could probably find the mass of a planet. It was one of your homework questions. I'd have to give you everything else for you to do so, but you could find the mass of a planet. You could definitely find the velocity. We've done that in class. Maybe if you could measure the velocity, you could find the radius of curvature. These are all things that you could do with the information that's right here. But I also want to point out, if it's a circular orbit, then you could do something else. For circular orbits, we know the path made is a circle, which means we could work in the period of the orbit. This is only true for circular orbits. We did this in class already, but I'm reminding you, this is the stuff that's special when it comes to a circular orbit. It allows for all of this math, it allows for all of these assumptions to be made. But today I want to talk about elliptical orbits. And elliptical orbits, although we've talked about them, you have to be able to be flexible with your understanding. What I want to talk about is comparing an elliptical orbit to a circular orbit. Let me get this out of here so I have less in my way. That should be good enough. A common question on the exam is to talk about an object that's in a circular orbit and then have a sudden change in the object's velocity. Now, to be honest with you, this discussion is about how you change orbits. That's what I want you to know when we're done here. How you go about changing an orbit. What happens if you change the velocity of the ship in order to change the ship's orbit? This is how you bring something back from being in orbit. It's how you send something out from one orbit and make it go to another. So this is what I need you to know. The first example, and we're going to call this case 1. A sudden slowdown. So we suddenly slow down the velocity of the ship. This would happen if the ship were to turn around and suddenly fire its jets and reduce how fast it's going. If that were to happen, the important thing is the velocity gets smaller, so it's less than it was before. This is the new velocity, and it was that big, and now it's smaller. The force of gravity on the ship doesn't change. So it's still being pulled downwards with the same force, but it's suddenly traveling slower, so its path is going to curve more sharply. This creates a new orbit. Assuming it doesn't crash into the planet, it will create a new orbit. This new orbit still has to meet certain parameters that we've talked about. First, trying to do as good a job as I can drawing this orbit, so let me do a slightly better job. There we go. So if you're to suddenly slow the object down, it would have to create a new orbit. But remember the parameters of elliptical orbits. Whatever's being orbited has to be at one of the focuses. Has to be at the focus, not the center. Has to be at a focus, not the center. You're going to be asked to pick out pictures, and you're going to pick the ones that you think are right, and they're not going to be right. Because you'll pick the one where the object, the planet stays at the center. Students always do, and it's always wrong. But in all orbits, the thing being orbited is at a focus. A circle only has one focus, but an ellipse has two. Not all of you know that because you haven't gotten that far in your math class. But you need to know it here. So if you suddenly slow down, that becomes the apogee of the orbit. The farthest away point. If you have a sudden slowdown, that becomes the apogee of the orbit. And the ship will now begin to accelerate and go faster and faster until it makes it to here. This point is called the perigee. And although we talked about these already, this new orbit is elliptical and travels inside the circular orbit. Now, obviously, if you make this orbit small enough, you hit the planet. That's how you bring something back in from orbit. But if you make this velocity a little smaller, you can transition from a higher orbit to a lower orbit. Now, you can stay elliptical if you want, or you can make a change to the object's speed at the perigee and suddenly have a smaller circular orbit. This is how you change orbits. This is case one, a sudden slowdown. I think you guys are probably pretty capable of predicting what I'm going to talk about next, right? So let's talk about what we're going to talk about next. Case two. All right, so spaceship again, right here at the top, has a tangential velocity, still being balanced by an acceleration towards the center, has a sudden speed up, so that the new velocity is this big. Look, let me just draw it in there real quick, and then we'll talk more about it tomorrow. But it's going to have to fall outside of the orbit it had before. It's going to go further away. It's traveling faster now, and the acceleration isn't enough to stop it, which means in case two, this becomes the perigee. Sudden increase makes that the perigee, the point of closest approach. And the ship will make it out to this point out here, the place further away, which is the apogee. All right.